Without further ado, my wonderful task to welcome you to Durham University this morning, to the Physics Department. You're more than welcome to the 2023 Christmas lecture. This year will be presented by Professor Ifan Hughes, who's the very proud Welshman there, and Dr. Stephen Wrathmall. Just a few words about these two gentlemen to show that they've got some legitimacy here, you know, although let's pretend, yes. So, Professor Hughes was born in the Rhondda Valley in South Wales. He studied physics at Imperial College and then got his doctorate at Oxford. I don't know where that is, but someplace down south. Oxford University in 1993. Following periods as a postdoctoral research assistant at Yale and Sussex, he came to Durham in 1999, and he's the current head of the Quantum Light and Matter Research Group. Sounds really impressive.
Thank you.
Ifan has made significant research contributions to 4 distinct fields of atomic physics: magnetic atomic optics, spectroscopy for laser stabilisation, quantitative atom-light interactions, and laser spectroscopy in large magnetic fields. I have no idea what that means. More importantly, he was elected a Fellow of the Learned Society of Wales in 2020, and that's a big deal, trust me. Stephen, is also a member of the Quantum Light and Matter Group at Durham University, where he completed his PhD in 2007, so he got his doctorate here, in fact. And since then, he's worked in academia around and about the place, and he also spent time working as a physics teacher. He's a local lad. He was born in Sunderland, and it says here where he is blessed in supporting the mighty Sunderland AFC.
Blessed, maybe questionable.
Well, we've all got our crosses to bear in life, right? And he grew up around Durham, so he's been in and around Durham for a long time. Stephen's research interests are in atom-light interactions with applications in magneto-optical filters. I still don't know what that means. And in recent years, he has focused on applications in solar physics. So that's where these two guys are going to talk to you about this morning. So without further ado, welcome you to Decoding the Spectrum, Saving Civilization from Solar Storms. Thank you very much.
Okay, morning, everyone. Just to follow up on one thing Pete said, so I'm from Durham, really. I was born in Sunderland. And more importantly, I'm from the northeast region, of which all of you are as well. And historically, we're a region where we don't have the greatest uptake in physics degrees, physics undergraduates. So I'm hoping, after today's lecture, if you haven't realised already, that physics is a subject that you might want to study, a subject for you. And after you've had a look around the place and maybe done some lab tours, you realise that Durham might be a place for you as well. So hopefully we will see some of your faces over the next 2 or 3 years. Okay, so today's talk is to do with the sun. Okay, so I want you to think about a sunny day, a nice sunny day, and what the sun looks like. And let's be honest, if in the northeast of England, it's probably going to look something like that. But let's imagine we're somewhere a bit sunnier. So you might think the sun is a very bright disk, rather static, uninteresting object. My daughter earlier on in the year, around springtime, decided to draw a picture of the sun, which I thought was mildly terrifying, actually, when she first did it. It's a pretty scary looking object. But in actual fact, it's probably closer to what the sun looks like rather than our traditional yellow disk. So we're very fortunate these days that we have lots of nice scientific instruments and can look at the sun in many different ways. I'm just going to turn the lights down a little bit. It seems brighter than it was yesterday. Okay, so this is the sun. That's definitely not a boring static disk. That looks very exciting. And that's because we're viewing it in a particular range of light. So we're viewing that sun there in a narrow part of the ultraviolet part of the electromagnetic spectrum. And that still looks quite static. So if we take advantage of some very nice instruments, so this is a satellite that the European Space Agency and NASA and other people put into orbit about 10 years ago, the Solar Orbiter. We can take those images, but we can also take films. So this film here, this movie, is taken over the period of about a day. So you can see there's interesting behaviour around the edge of the sun, so we can see the edge very nicely. We can see flashes and other things. What I really liked about this probe when it came into operation was they took movies as it approached the sun. So this isn't zooming in an image. This is the actual probe zooming in towards the sun. So that was, I think, a period of about 20 days or something. So the sun, in actual fact, is a very exciting and dynamic thing to look at. It's not this traditional boring yellow disk we often think about. Turns out we know a lot about the sun already. So we know the mass of the sun, we know the size of the sun, we know about the fusion processes that drive the heat and light of the sun, and we know a bit about the structure of the sun as well. So we know lots of things, we still don't know some things, but the parts we are interested in today on this stellar, very hot onion are these two layers here. So the photosphere and the chromosphere are two atmospheric layers that are transparent, that lie above the sun's surface. So the things we're going to be talking about today, the atoms we're going to be exploring, all live in these two regions here above the solar surface. Now, I said the sun was very interesting. And it's very interesting because, firstly, the sun is a plasma, so it's made of charged particles. And as a consequence, there are lots of interesting magnetic field effects on the sun. The fact that these are driving magnetic fields in the first place. So, think of your left-hand rule, and you've got charged particles and magnetic fields. They can do lots of interesting things. So we have things here called prominences. We have things here called flares. And we have things here called coronal mass ejections. And these are the things we're really worried about. So technically, a flare is an intense burst of electromagnetic radiation. That's what the flare is. And that takes about 7 minutes to get here from the sun to Earth. The coronal mass ejection is the sun flinging out billions of tons of these charged particles out into the solar system. And if we're very unlucky, one of these things might head in our direction. Now, it's also worth noting that often you get these two things at the same time. So often you don't just get a flash, you get some matter flung out as well. So we can do some really nice simulations on this using real data as well. And this is an example of a prominence. So for prominence, the matter remains attached to the surface of the sun. So you get these nice loops and arches. There's an example of a flare here. So at the top is that bright flash of light. That's the flare, but you can see there's also some mass ejection there as well. And then the things we're more concerned about are these things here. So that's a coronal mass ejection. So that's a huge amount of charged matter that the sun has ejected out into space. And, I presented them as isolated things, but in reality, if you were to look at the sun over the period of a day, you have all these things, going on during that day at the same time sometimes. So we've got prominences on the edge of the sun, we've got a flare and some mass ejection. And if I keep talking until we get to 8 o'clock, you'll see something a bit more exciting here. So this region's starting to get active, and it's going to... I'll just keep talking. I think it's called filibustering, isn't it? It's going to fling out some stuff into space, so a mass ejection. So these things are happening all the time. So why do we worry about them from the Earth's perspective? Well, let's consider our nice little pale blue dot. And we know that Earth has a magnetic field, and as these particles approach the Earth, so I feel like we should have some ominous music here, it interacts with the Earth's magnetic field. And you'll be familiar the effects of that phenomena, of these charged particles interacting with our Earth's magnetic field, because they drive things like the aurora borealis, so the northern lights, in this case. And there's some beautiful footage. We're blessed these days of all the nice footage you can find. This was taken from the International Space Station, and you can see these really beautiful aurora over the northern part of Earth. And you can even see it from Durham. So this photo was taken by a very basic webcam we used to monitor the weather for our observatories on the department's roof. And on the 5th of November, there had been some intense solar activity days beforehand, and we got to see these aurora. And I've seen many more beautiful images of this in the region as well. So we do see the effects down here. Okay, so aurora are pretty. We should just be happy, shouldn't we, that we're getting these things and getting beautiful aurora. But space weather can have serious consequences. So there are a couple of historic examples of what can happen. The first is from 1989. So in Quebec, there was an intense geomagnetic storm. So there had been intense solar activity days beforehand. And that led to a blackout of Quebec for 9 hours. It was so severe that the stock exchange in Toronto had to close. It takes a lot to shut a stock exchange down. And that global military operations, because these things interfere with the electrics, various things, were affected. Planes had to be grounded. Power and infrastructure had to be repaired. There was a coronal mass ejection in 2012 that missed us by 9 days. So as we're going around, orbiting around the Sun, this thing missed us by 9 days. If it had, it was such a large event, they estimate the economic damage would have been something in the region of $0.6 trillion to $2.6 trillion. Huge, huge costs. You know, you're talking immense damage to the power networks. And what do we all rely on? We rely on power networks. People think about this a lot. People run studies, write journal articles. We can all sleep well at night and know our government has a space weather preparedness strategy. And as scientists, there's money. There's money available to study these things. So it's a great interest. I'm going to very quickly mention the most severe and intense geomagnetic storm in history was the Carrington event in 1859. It's mentioned a lot. Now, fortunately, there wasn't a huge amount of electrical infrastructure. It was mainly telegraph lines, but it was so intense that the telegraph lines fried, and the telegraph operators were actually getting electrocuted from it, the size of the currents that were induced. And one of the reasons I mentioned this is a colleague of ours, Professor, pointed out there's a link between Richard Carrington, who it's named after, and this university. So he was actually the observer of Durham University before that event, so that was a position he held. What I love about it is I've shown you nice fancy satellite images, monitoring sunspots and things. This is the intense region that led to the Carrington event. So Dr. Carrington basically made images of the sunspots days beforehand, and then this big event happened, and he published it in a journal like we do as scientists. So you've seen the state-of-the-art simulations go back 150 years, and that's what it used to look like. And it's quite topical as well. So we didn't arrange with the press to do a story like this just before the Christmas lecture. So Monday the 11th, the Daily Star pointed out that our train infrastructure in this country is at risk from solar storms, which is going to be sorted out by the Boffins, which I think we're the Boffins. Yeah, we're the Boffins that are going to sort that out. Okay, and finally, if we want to understand what drives this phenomena, if we want to be able to make accurate space weather forecasts, so if we want to know that something like this is coming, so we can turn things off, we can ground planes, etc., we need to understand magnetic fields. So be very familiar with this idea here of the Earth's magnetic fields. This is a simplified picture, but it works quite well. The Sun, on the other hand, is much more complex. And if I want to understand what the magnetic field's doing here, where there's lots of sunspots in this active region, it's much harder to work out. I've got to do lots of simulations. And to get accurate simulations, so I can get accurate space weather forecasts, I need to know accurate input data about the magnetic fields on the Sun. And that's what we try to do. That's our goal, to give the people who make these simulations accurate information about the magnetic field within the Sun. Because if we want to make better space forecasts, so if we want to predict solar weather, we have to understand the solar magnetic field. And Professor Hughes is going to guide you through some of the concepts we use to do that.
Thank you very much, Steve. So, yeah, I'm a quantum physicist. I'm a boffin technically, but I'm definitely a quantum physicist. And in our research group in Durham, we study the interaction of atoms, lasers and magnets. And as you'll see at the end of the talk, the reason we're doing that is the motivation of solar studies. But in this middle fraction of the talk, I'm going to tell you about some concepts that are important for understanding how our instruments work. And I'm going to try and demonstrate most of the key concepts with various activities, some of which are simplified and you could, in theory, do at home in your own kitchen. So let's see how we get on with that. So the key concept we're going to start with is the idea of spectral lines. So if you have atoms, you heat them up, they might emit a certain range of colours. So everyone should have, at the end of their row, if they aren't, pass them along, please, a diffraction grating. And then the extreme generosity of the physics department, you can keep the diffraction grating. Ooh, yeah, that's right. Well done. So while the lights are still on, the orientation you want to use them is, there's a side and it says thousands lines per millimetre. You should have that facing towards you. There's a little axis in the bottom. And then I'm going to turn on a lamp in a second, and your instinct is to look straight at the lamp through the diffraction grating. The light's going to diffract a lot by like 45 degrees. So actually one of the easiest ways to see these lines is you're going to look at the lamp and then turn your head by about 45 degrees, and we should see some lines. So if we turn on neon. Oh, that's darker. Okay. So my prescription was you want to look at the lamp and then turn your head off by about 45 degrees, and you should be seeing an intense set of lines. Anybody seen an intense set of lines? Quite a few red ones and orange. So that the atom in that lamp is neon. So neon atoms, when they excite, they emit a certain set of colours. Your eye interprets that as red. This simple grating, diffraction grating, allows you to see that actually there's more going on, but they are discrete lines. Another interesting element is mercury. So the lamp will warm up a bit. That looks maybe white, slightly blue, but it isn't a smooth white line distribution. So same trick, start the mercury lamp, tilt your head off by about 45 degrees, and you should see a very intense green line. And then mercury also has yellow, blue, and all of that adds up in your eye to look bluey white. And people see the intense.
Yeah, I can see yellow.
Yeah. Can you see a very intense green?
Yeah.
And there's a yellow. Yeah. Can you see them, Edwards? You're not even trying over there. Yeah. Excellent. Oh, slightly dimmer. Yeah. Okay, so what's going on there? The idea is, you heat a lamp. If you have isolated atoms, they move around, they collide, they get excited, they emit radiation. And the radiation they emit is like a fingerprint. So certain atoms have certain patterns, and you can use this to work out what things are. Hydrogen is the simplest atom, and it has a very simple spectrum. We've just been looking at neon, which is lots of intense red, orange, and a yellow line. Sodium is the lamp we have over there, which is mostly orange. We'll see that in a few minutes. And we also saw mercury. So your eye perceives mercury as white or blue, but actually there's an intense green line, a yellow line, some turquoise blue, and some reds. Okay. So why are there discrete lines, not a continuous distribution? So you need some quantum mechanics to explain that. So Niels Bohr came up with a model of the atom, and it was absolutely crucial in the development of quantum mechanics. You might have come across some of these ideas in A-level physics or in A-level chemistry with shells. Electrons can only live in certain shells, and then when they fall down from a higher level to a lower level, they emit a fixed amount of energy, and then we see that as discrete lines. So the reason that atoms have these beautiful, simple, discrete spectra is a manifestation of quantum mechanics. So quantum mechanics allows us to make predictions about the properties of atoms when they're isolated and they absorb or emit light. Okay. The other thing you can use your diffraction grating for, can we have the main lights back on quickly, Steve? So look at the white lights in the ceiling through your diffraction grating, and you should see something very different. So it's an extended source, unlike the lamp, but the biggest difference is you should see the spectrum is spread out. Are we seeing a smooth spectrum? Is it spread out this time? Brilliant. It works. Yeah. Okay. So that's another regime of atom-light interaction. So in the lamp, you've got a solid material. Atoms are crammed in. They interact together strongly. The discrete lines disappear, and you get these very, very smooth spectra. And again, in the history of quantum mechanics, this was known as black body radiation, and understanding this was very, very important historically. So for a source, essentially, it doesn't matter what it's made of. Unlike the atom lamps, they all emit the same shape, and the only thing that adjusts the shape is the temperature. So I've plotted some of these black body radiation curves here for 4,000 Kelvin, 5,500 Kelvin, 7,500 Kelvin. 5,700 is an excellent approximation to what the surface of the sun. Steve was telling you about the photosphere. If you were just above the photosphere, you would expect to get a smooth distribution and lots of red, orange, yellow, green, blue, indigo, violet. And then it's not an accident that that's what our eyes are really good at seeing. And we've evolved into seeing that spectrum with that distribution, and we think of that as white. So white light is that smooth distribution that the sun emits. But then there's a more interesting question. If you have some isolated atoms, and you also have the same species of atoms emitting light, what will happen if you try and pass the light from some atoms through some other atoms? So for that, we need to put on our goggles. You're safe, don't worry about that. I think the people who helped us yesterday, they're out of hospital now, Pete, is that right?
Say again?
The people who helped yesterday, they're
out of hospital.
Great, that's all right, don't worry. Yes. So, what are we about to see? The lamp is a sodium lamp. It's emitting those bright orange lines I showed you 2 minutes ago. And as you can see, the light is currently flooding onto the whiteboard, and you can see orange light. There are a few metal things in the way, and the metal things cast a shadow. So the reason you're seeing a shadow of the stand on the white screen is because light doesn't go through metal. Light, however, does go through flames. So we've now introduced a flame, and as you can see... Ooh! Calm down, Jason. Calm down. So flames don't have shadows. The orange light goes straight through that flame. Right? There's no hint on the screen that the light's been absorbed, because unlike metal, the light goes through the flame. And then when it settles down, we're going to introduce some sodium into the flame. So that's a stick of chalk that's had some salt solution in it, which will introduce some sodium atoms. And now, look at that. The flame has a shadow. So why is there no light? Light, no light. So it's not the flame alone that does it. So if you take the chalk out, Jason, thank you. So the flame alone, clearly the sodium light goes straight through it, and introduce some sodium atoms. It's a dark flame. So why is there now a shadow? It's because the sodium atoms in the flame interact very strongly with the sodium light emitted by the atoms in the lamp, and as a consequence they don't go through. And we're all alive. So thank you very much, Dr. Anderson. That was the hairiest one we've had so far. So here's some photos to illuminate that concept. So if you're a sodium atom and you're in your ground state, if you're illuminated with white light, you're likely to absorb on these resonances between the discrete energy levels. So the light that goes missing is the bright orange light. And at the same time, if you hit some sodium atoms and they're excited because they're in an electrical discharge in that lamp, they'll end up in excited states, and when they fall down to lower energy levels, they emit that orange light. So it's not an accident that the emission line of sodium, this bright line, exactly coincides with that dark band. Because as you've just seen, sodium light does not propagate through a medium where there are sodium atoms. It goes black. So this is the spectrum of the sun. So 5 minutes ago I told you the sun had a smooth black body-like spectrum. This is a phenomenally high resolution. So the same principle as a diffraction grating. Huge resolution, which means it spreads the light out. And then these are splitting the spectrum into 50 bits. So the reddest part of the spectrum is at the top left, and the bluest part of the spectrum is at the bottom right. And then cutting the spectrum into 50 bits and stacking them vertically. And what you see is, it's an excellent approximation. There's a lot of red, a lot of orange, yellow, green, blue, indigo, violet. You add all of that up, that's white light. However, you also notice that there's gaps. There are dark lines. So there are 2 dark lines in the bright orange part of the spectrum. So what are they? So if we had a higher resolution spectrometer, we would see that the orange light from that lamp is 2 very close neighbouring lines, known as the sodium D lines, and there they are. So the sodium D lines appear dark, from which we infer there must be sodium atoms in the chromosphere. In Steve's onion picture, the photosphere emits the light, and the chromosphere is for the next 1,000 kilometres above that. So we learned there must be sodium atoms in the chromosphere, because just like that flame demonstration, they absorb that light and disappear. And then each one of these other features, some are much more prominent than others, you can then use the fingerprints of the atoms to work out what's on the sun. And actually, people worked out that there had to be helium on the sun, because it comes from the Greek word for sun, before helium had been found on Earth. So analysing spectra of an object that's 93 million miles away led us to understand more about the structure of the sun than we knew previously. And that concept's going to be really useful for us. We need to measure the magnetic field of an object that's 93 million miles away, and the idea is the light that gets transmitted to us here on Earth, we can do experiments here and learn something about a very remote object. So the scientist who first discovered this phenomenon, after he built a high-resolution spectrometer, was called Fraunhofer. So that's the textbook Wikipedia Fraunhofer diffraction pattern. So here, one line rather than 50 segments. Here's red, here's blue, and then you see these prominent absence lines. So there's the sodium D lines again. And you can just about do this if you've got a decent camera and a diffraction grating, as Steve did, and that's Steve's Fraunhofer diffraction pattern from the sun. Okay. So the solar spectrum's got a lot of information, and we can look at it in different bands. So we've seen similar photos already. So that's a montage of looking at the sun in different colours, basically. And that's another montage. And you can use narrow filters, and you can look in the red, and you can look in the green, and that's all very nice. But what we're interested in is learning about these solar storms. So the question is, how can we learn about the magnetism of the sun by doing something with light on Earth? Right. So that's the question. How can we measure the magnetic field of a remote body? And the answer is there must be something about the magnetic field that's encoded into the light that gets to us. Okay. So I'm going to now explain to you a concept known as magneto-optical rotation. So the magneto part is because it's caused by magnetism. And the optical rotation is a phenomenon to do with polarized light. So we're going to have a brief diversion into the properties of polarized light, and then I'll show you how we use something known as the Faraday effect in order to analyze polarized light, from which we can infer the magnetic field in the sun. Okay. So let's start some of these demos. Polarized light. This lamp doesn't emit polarized light. Most sources don't. They emit light that is oscillating in random directions. And if this is a sheet polarizer. If I put my sheet polarizer there, that thing only lets light through that is oscillating either up and down or horizontal. So after that polarizer, the light is beautifully horizontally polarized. And if I find my second sheet of polarizer, if I arrange it to be parallel to the first one, the light that came through the first one will then also come through the second one. So this is slightly grey compared to what it was before, because half the light didn't make it through the first polarizer. But when I add the second Polaroid in the same orientation, basically nothing happens. But if I make the second polarizer orthogonal to the first one, the vertical beam transmitted by the first one will not go through the second one. So it should go dark. Yeah, like that. Hurrah! Okay. So that's simple ideas about polarized light with linearly polarized light. What's really useful if you're thinking about atom-light interactions is to think about circular polarized light. So you can also make light waves. They propagate towards you in vacuum at the speed of light, and as they're going around, their electric field traces out a helix. And there are two kinds. There's the one that follows your left hand, so left hand circularly polarized light, and you also have the one that follows your right hand. So you can have left or right circularly polarized light waves, and these have an electric field that spirals as it moves through space. You could have two beams at the same time, left and right, simultaneously coming towards you. That's easy to arrange. And because these are their vectors, the electric field, you can add two vectors, and that's what I'm doing in this animation. So I've started the clock when both of the fields are in phase at 9 o'clock. And then one's oscillating clockwise, one's oscillating anti-clockwise. And what you find is, so at 9 o'clock they're both in phase, so they add. One does a quarter of a turn, so it's at 6 o'clock. The other goes to midday, so they cancel, so there's nothing. Then they both add up at 3 o'clock, etc. So this grey line is, in fact, linearly polarized light. So linearly polarized light, which just goes back and forth along the horizontal axis, is, in fact, a combination of left and right circularly polarized light, both propagating at the same time, at the same speed. So that's in vacuum. So imagine I have a box in which I've got some medium, and at the minute the medium's nothing. So if the speed of light of the two hands is exactly the same, if you put in linearly polarized light, you'll get out linearly polarized light. But something much more interesting happens if in this box I have a medium, and in the medium, left circularly polarized light travels at a slightly different speed to right circularly polarized. And when you add the two vectors with the clocks going round at slightly different rates, what you find is this. The grey line is the sum of the left and right, and it is still linearly polarized. So when it leaves the medium, it's oscillating along one plane, which is the definition of linearly polarized light, but the plane along which it oscillates is now 45 degrees rotated. So this is the phenomenon of optical rotation. I start with light that's oscillating horizontally. I put it into a medium. The light is still oscillating in a plane, but the plane has rotated. And the way to think of that is in terms of the difference in speed between these two circular components. So if I forget about the circular components, that's conceptually simpler. All I'm doing in this experiment is putting in linearly polarized light. I need a medium where left and right propagate different, and what comes out is rotated. Okay. So that's optical rotation, and there are two obvious ways you can generate optical rotation. One is with a large magnetic field, which we'll get onto in a second, and the other is an experiment you can actually try at home in your kitchen, in fact. So that's just summarizing. Linearly polarized light you actually want to think of as left and right. When linearly polarized light goes through a medium, if the speed of light is different for left and right, you get a rotation. And Faraday first discovered this for magnets, but we're going to look at it in another medium. So we're looking for a medium where the speed of light is different if you're doing this versus if you're doing that. So we need a medium where the individual entities in the medium know the difference between left and right. And the question is, what is that medium? And the answer is here. So here's a clear fluid. Doesn't look terribly exciting. So if you can see it in transmission, it's basically straw coloured. If I pass some light through it, nothing terribly exciting happens. It still looks, it's settled overnight. It's a syrup, which is why there are some ripples in it. That's not a big deal. So light comes through this thing. Your eye still sees it as mostly white, sort of slightly yellow. It doesn't look that exciting. What's actually going on in the corn syrup is made up of glucose molecules, and nature makes left-handed glucose molecules. It doesn't make right-handed ones, which means the speed of light is different for left circularly polarized versus right. So what we would expect is different colors coming through that corn syrup have actually been rotated. Now your eye can't see that because you don't have polarization vision. But if I find the sheet I've already lost, it's in the dark. So I've linearly polarized my light. I've put it through a medium. Nothing terribly interesting happens. I'm now going to add the second polarizer. And last time we either saw the same intensity or nothing. And this time we should see something more interesting. Look at that. So that's changed its colour, and if I make small changes to the angle of the second polarizer, I can dial up different colours. So I can make yellow, I can make a more intense orange, I can make no idea what that colour's called. There's that one. That's official Durham University logo colour. That's the university will be delighted I nailed that one. That's a more intense purple. That's blue, etc. That's probably turquoise. That's pale green, etc. So all you need for this demonstration is some sugar solution, corn syrup, available on Tesco, I believe. Jason, is that right? Sheets of Polaroid. If you don't have sheets of Polaroid, you've probably got them at home in polarizing sunglasses. And then you can demonstrate this optical activity and also make the world's cheapest disco, where you can just dial up any colour you want at any stage. I think that's my favourite shade. Look at that. There we are. Great. Thanks. So that's the phenomenon of optical rotation. This is some data taken a few years ago in our undergraduate teaching labs. So we published a paper because we had analysed the colour coming through. That's a lamp looking through corn syrup, and then you see 4 very different shades. So a student called Miranda worked with me, and the results we got were so conclusive that we published it such that other scientists in other countries could see what they were doing. We also collaborated with Jason, with a few other students, to do a simple experiment. We have a white light source. There's our polarizer. For this experiment, we didn't even get the corn syrup out of its jar. That's a jar of corn syrup. There's the second polarizer. And then rather than using your eye to judge colours, which is very hard to do, we did a slightly more quantitative scientific investigation by having a spectrometer. So I'm about to show you. So it's a similar device to that diffraction grating, except there's a camera that takes pictures of the different colours and a computer that tells you what the colours are. So I'm about to show you some spectra of what comes through this sugar solution. And the reason the sugar behaves so interestingly is, nature makes one hand of sugar molecules and not the other. So all that's going on is the speed of light is different for left versus right circular polarization. So that's the spectrum of our white light source. You get a bit of red, orange, yellow, green, blue, indigo, violet. We carefully adjusted, we found the right thickness jar, the corn syrup such that in the green part of the spectrum, you expect this optical rotation to be 90 degrees. So then if you have your parallel polarizers, the medium in the middle rotates the light by 90 degrees. So for green, you would then expect a deep notch. Okay? So the light will disappear in the green, and you'll squash down neighbouring colours, but you let through red, bit of orange, and some of the blue. And the question is, what would your eye then perceive? So that's the initial light, that's the optical rotation. Here's the spectrum after the sugar solution. And then there's very clever software where you say, this is my spectrum. What colour would I see? And that square in the top right-hand corner there is the output from that Python code that says you would see orange. And then as I rotate my second polarizer, this notch moves along. So I can make the notch in the green, I can make it in the orange, I can make it in the yellow, I can make it in the red. And as different parts of the colour of the spectrum are eaten up by the sugar solution rotating the light, you would expect to get orange, then purple, then blue, then green. And those red, those round pictures are photos from the lab. So the prediction was we'd get those colours in the squares, and the measurements are the colours in the circles. And as you can see, they agree phenomenally well. You can also turn it into a movie. This is looking along the direction of the light. As you rotate that polarizer, you see the notch gets eaten up. Our spectrometer tells you where the notch is. And then white light minus a lot of red, for example, is that sort of pale green. The notch is now in the infrared, which means our eyes don't see a big difference. It's mostly yellow, straw-coloured. And then in a second, the notch will come back around to the blue end of the spectrum. And when it starts to eat the blue, you'll see much more coloured illumination. So as the blue disappears, it gets more yellow. And then as the notch moves along, it turns into a deeper orange. When the notch is in the green, it turns into that beautiful red. When the notch gets over there, purple, turquoise, whatever that colour's called, cyan, etc. Okay. And one other thing I should have pointed out about this slide, sorry, here. This work we did with another professorial colleague of mine is on the paper, Jason is on the paper, and we have two undergraduate co-authors. So they were undergraduates in our second year lab. They discovered this phenomenon and how you could look at the different colours in their kitchen. And then we did a scientific investigation and we published that. I'm sure we didn't that. Sorry, there it is. I'll get it right in a second. Yeah, so that's Jason, that's me and a professorial colleague. So Jackie and Catherine were the undergraduates who helped us do this experiment, and we've published that result in a journal known as the American Journal of Physics, such that other people around the world can also benefit from our insight. So let's go back to the sun. We've now hopefully convinced you that optical rotation means colours become more interesting, objects have information encoded into their polarization, and the question is, how does a magnetic field encode information into the polarization? And for this, we're going to look at this picture. So remember the Fraunhofer D-lines, the bizarre thing about the experiment we do, what we're actually sensitive to is the absence of light. It's dark lines. Light goes missing. So this is potassium, our favourite atom. And potassium has a D-line, and at its centre there's a dip. So no light comes through the photosphere because there's potassium atoms there. And that's when they're not in a magnetic field. And the question is, what would happen if you add a magnetic field? So here's a spectrum, an atomic spectrum. Under the presence of a magnetic field, you get splittings. So the energy levels split. Some go up in energy, some go down in energy. So that's known as the Zeeman effect. So the Zeeman effect shifts the energy levels of the atom. And as a consequence, the light that's emitted, you get more or less left or right circular polarization. So in this simulation, I'm showing what would happen to the Fraunhofer line if there was a magnetic field on the sun. And what you see is it splits. And light from this end of the spectrum is going to be more left-handed, and light from this end of the spectrum is going to be more right-handed. And then our friends at the European Space Observatory have made a far more fancy movie than we can, so let's watch that. So that's the sun, not terribly magnetic at the minute. You get as much left and right circular polarization. So magnetic activity happens, the magnetic field is ramped up, sunspots appear, the spectrum splits, that's the Zeeman effect. And now, if you look at one particular colour, you get much more handed light from one helicity than you do from the other. So the magnetic field on the sun is associated with these solar sunspots, and crucially for us, the light that's emitted towards us on Earth now has much more handed light in it than the other. And what I've just shown you with the corn syrup is that will lead to a rotation of the plane of polarized light. Okay. So we're going to essentially use that phenomenon to measure the separation between these Fraunhofer lines. If we can measure the separation, we can then infer on Earth a magnetic field 93 million miles away. So what would be really good at this stage is if I could replay the dark flame experiment and I could add a large magnetic field. So we need large magnetic fields. The sun makes magnetic fields of the order of a Tesla, which is far larger than you see in your everyday life. And wouldn't it be nice if we replayed the sodium experiment now and brought in a giant magnet, and then we would Zeeman split the line and the shadow would go away? And the answer is yes, that would be brilliant, but it's technically illegal. So we can't have the large magnet, which is water cooled and uses 20 amps, in the same room as 200 school kids. We did ask, but we were told no. But under very safe conditions in a teaching lab last week, Jason managed to film the experiment. So I'm about to show you a film of what I've just described. It's basically the same experiment as here. You'll see a sodium light, you'll see a large magnet, you'll see a flame, and when the magnet is off, you'll see a shadow. And the prediction is, when I crank up this magnetic field, the Zeeman shift will let the light go through. So let's see if that happened. There we are. So there's the flame, there's the magnet, pole pieces. The magnet is currently off. That's the shadow. So we're looking at, the reason that's black is the sodium atoms in the flame have absorbed the sodium light from the lamp. And the fact that the magnet is there hasn't perturbed it at all. We're currently drawing no current, no magnetic field. So if we pull, is it playing? So as we crank up the current to 20 amps, danger levels high, the magnetic field comes on, and I hope you can see the shadow went away. So there's the shadow, no magnetic field, total absorption by the sodium atoms, Zeeman effect, energize the magnetic field, the shadow goes away. And why is the shadow gone away? Because these sodium atoms are now not on resonance with the sodium atoms that's emitting the light, because they're sat inside that very, very powerful electromagnet. So, drawing to a close my contribution to this, quick summary, it's the Faraday effect that's associated with magnetic fields that causes optical rotation. You can think of linearly polarized light as equal amounts of left and right circularly polarized light. This device is known as a Faraday filter, and you cross your polarizers and rely on atoms rotating the light such that you can see atoms only from a very, very narrow spectral region. And the effect was first demonstrated by Michael Faraday many, many years ago. And it's one of the first demonstrations of electric fields, which is light, interacting with magnetic fields, which was absolutely crucial in the development of electromagnetism. That's one reason why Faraday is so famous. What do we do on Earth in our labs around the corner? This is a busy slide. It's basically a research slide showing. So what we do is we have lasers, atoms, magnets, cells, and we study how to make Faraday filters. And in Durham, our expertise in the quantum light and matter group is in making ultra-narrow atomic filters. In fact, we make the narrowest atomic filters of anyone in the world. So that's why we're involved in this project. So we want to make profiles that are spectrally extremely narrow, such that we're very sensitive to the magnetic shift of this optical rotation phenomenon. And then you're going to love this, Pete. This is my last slide. It's a lot of the phenomena I've just shown you involve thinking about light. And I think about light a lot. And it's getting to that stage of year, you need Christmas presents, you've got a male relative. What do you get an uncle who doesn't like things? Well, I'm going to suggest you get him a book. And maybe you could get that book. And it's my favourite book about light, largely because I half wrote it. It's brilliant, to be honest. It's absolutely fantastic. What it does have, why am I showing you that picture, apart from it's a shameless plug? In the book, if you wanted to learn about polarization or optical rotation or dispersion in sugar solutions, you will find a lot of beautiful colour photographs, and they all have one thing in common. The people who helped Professor Adams and me take all the data to populate the book with colour images are people like Miranda, Jackie, Catherine earlier. They're Durham undergraduates. So if you come to Durham to study physics, not only are you taught by the people who wrote you the textbook, you might actually contribute to the next generation of physics textbooks. And with that, I'll hand you back to Dr. Wrathmall.
Very much. Okay, so let's think about what we've done so far today. So hopefully you've seen the motivation of why we are interested in this. We've looked at the concepts and the phenomena we exploit to help us calculate magnetic field strengths. And now we need to build something to do this, something practical. So what we do here at Durham is we've been involved in building a telescope, a solar telescope that will allow us to measure the magnetic field strength at various points on the Sun. So what we do when we build these things is we start with a diagram, and this bit at the start here, as in the lens, that's the telescope bit. And the stuff that follows is the magic bits. So the things in the dashed grey boxes are what we build here at Durham. So Professor Hughes mentioned these magneto-optical filters. Essentially within these grey dashed boxes there are just magneto-optical filters, so don't worry about the parts in them. What they allow us to do is image in one type of polarisation, and then we can switch it so we image in a different type of polarisation. And if we do that, it can help us determine the strength of the field that's splitting those lines. So you see on that little picture there that as the field strength increases, the lines get wider. And this device here allows us to measure the strength of that field that's splitting them. Okay, so that's very theoretical. We can do lots of simulations and things, but then we have to build some things. So our colleague, Dr. Pizzi, designs and builds the magneto-optical filters for this instrument. And here they are getting tested in the lab. So our filters are essentially these things in these big chunks of brass. So there's large magnets in there, and there is a cell, an atomic gas, which we use. And here you can see it getting tested, so we've whacked the telescope on the front of that, and once all that's done and we're happy, we take it out into the field. So this is the telescope in the field, this is the telescope getting tested in sunny Durham, believe it or not, the sun was out. And again you can see these filters here, these big chunks of brass, that allow us to select what polarisation state we are interested in. So once all that was happy, we put it in a big wooden box, cross our fingers, and pray it gets to where we want to put it. And where we decided to put this instrument is in a place in Hungary, in an observatory on top of a water tower. So we built this observatory on top of a water tower. Why have we chosen that location? We've chosen it for its well-known exceptional seeing, so it helps us take high-quality images which are useful to us. And then we switch it on. So this is one of the very first images, working images we got from the instrument. And you can see there's some nice sunspots, some nice magnetic activity. And how do we know it's working? Well, we can compare any image we take at this telescope with images taken by other instruments. So one might ask, why bother with a telescope on Earth when we can take beautiful images in space? And one of the ideas is cost. Yeah, this thing is millions and millions, maybe $1 billion. The things we build, we're talking like tens of thousands of pounds, and we can exploit that later on. But we can use this to essentially check our homework, check our answer. And this image here was taken by the Solar Dynamic Observatory. That's the picture I just showed you before, using the helioseismic magnetic imager. So I think there's pretty good agreement there. We christened this the footprint image because we felt it looked a bit like a footprint. So if we want to work out the field strength, we don't just need one image, we need images in both of those polarization states. So you might think you just need 2 images. We actually need 4, so let's not worry about the 2 extra ones. But essentially, we're imaging in the left-hand polarization state and the right-hand polarization state. And we're doing that because we've exploited these magneto-optical effects that Professor Hughes was talking about before. Now, we can do cool things for those images, like add them and subtract them and divide them. And they look very similar, but they are not the same. So if we essentially subtract these images, we get something called a magnetogram. So this looks very different to the source images I've just shown you before. And this is essentially a magnetic map of the sun in the region where those atoms were emitting light. So this will be the magnetic map at a particular height in the solar atmosphere. And of course, we check our homework again. I'm hoping I can convince you, despite the fact that STO have used a false colour in this image, that they are roughly the same. So we can see these features here, high intensity magnetic features here, and they're there, and there's other interesting features here, and other interesting features here. So I hope I've convinced you that it works. And this is one of our more recent magnetograms, which we're very proud of. You can probably see the image looks a lot cleaner, and there's lots of nice activity going on there. So very useful to us if we want to make accurate solar weather predictions. Now, just as a side, I meant to do this morning as well, you can get magnetograms very easily, way easier than you could say even 5 years ago, by going on to HelioViewer and has access to lots of different instruments, lots of different satellites, telescopes based on Earth, and you can dial up solar images, magnetograms, Dopplergrams, all sorts of things at will. So I think that's pretty cool, and that's what the sun looked like yesterday morning. I was hoping to, I completely forgot, if I'm honest, did that. Okay, so we've got a telescope which can produce magnetic maps of the sun. Now what? Well, the idea is to have a network of these telescopes. So place these telescopes all across the planet. So we have continuous monitoring of the sun. So we're always looking at the sun in some region here around the globe. And we call that SAMNet. And that's what we're part of here in Durham. So we're wanting to design telescopes like what we've shown you before, in actual fact slightly more advanced instruments which are going to do extra things, and place them around the globe. And then what we do with the information from the telescopes is give it to the mathematicians, the solar physicists. I should point out we're not solar physicists. I feel a slight imposter giving a solar physics talk as an atomic physicist. But there you go, that's the brilliant thing about physics. You start in one thing and you end up working in another, and it's fantastic. So what the mathematicians do, they want to plot the field lines on the sun. So this beige rectangle here is the surface of the sun. And they want to model the field lines coming out of the sun. So this blue and the red are like the north and south parts of the bar magnet, between some sunspots. So they want to do accurate field lines coming out and going back in. And if they do that, if they have those accurate field lines, they have very interesting, sophisticated models that look for a signature. And if they see that signature, they know a solar flare is coming. Yeah, so they need this here, and they're looking for quite a very small signature. But if they see that, they can tell us that a flare is going to happen much earlier than we know now. So our outlook for our instruments. Well, in Durham, we've built a telescope which can do this. It can produce magnetograms. We can feed data to the mathematicians so they can put in their models. our plan is to continuously monitor the sun. And if all this goes to plan, we're going to be able to give an advanced warning of between 20 and 26 hours of solar flare events. That's a lot of time, yeah? You can ground a lot of planes, you can make preparations in your electrical infrastructure. The more warning time, the better. And that's it, that's what we do. So I'd just finally like to mention a few things. Firstly, science isn't done by individuals. Sometimes you might think that when you watch films and things. It's actually teams that do work. So in Durham, the Quantum Light Matter Group, we have Professor Hughes, who's leading the project, and me. So I'm involved in the theory, the simulations of these filters. We have Dr. Pizzi, who builds them, designs and builds the filters. We're very lucky to have a world's leading Centre for Astronomical Instrumentation. So these people work with NASA and other space-based organisations, and obviously that's very handy if you want to build an instrument. So we've been very lucky. So Professor Morris leads that group, and then we've had Joss and Tim and Jürgen helping to build the instrument. Like I said, we're working with solar physicists, mathematicians. So we have Robertus here, who's leading the entire project overall, who's the standard leader. And we work with Mariana and David. So you might note that they all work at different universities as well. This is, again, the great thing about science, international collaboration, to do really great things. And then we have our students working in the observatory in Hungary. But as I mentioned before, this is an international network with lots of people in lots of different institutions all around the world. And we must thank people as well. So I'd like to thank the people who've given us money. So APSRC, STFC and the UK Space Agency. This lecture would have never happened without the wonderful support from Jason and the other technical staff. Greg and his comm teams, again, thank you very much. I must thank the people who provided the magnets and John Dobson with his hammer. This would have never happened without his hammer, believe it or not. Pete and the outreach team, and our colleagues, Dr. Gallagher and Dr. Walker in QLM. And that's it. Thank you very much.
Can I just very quickly say two things, folks? Corn syrup is available from other supermarkets than Tesco, and there are many very good optical physics books available compared to...
Not going to be seen.
No, I mean, there was a serious point. It was a blatant plug.
Thanks.
But it was also a serious point because a lot of undergraduates did contribute to that textbook. So, you know, you can do physics and be in books even before you get as famous as these two guys. And on that note, yes, so we've got a few minutes, I guess, for questions. We've got some lab tours organised for quite a few of you, I know. But before we do that, would anybody like to ask a question of our two esteemed colleagues here?
The question was, how does the charged particles emitted by the sun interact with the Earth's magnetic field, and how do we see it? Yeah. The northern lights are a manifestation of... So the Earth has a magnetic field, which... if we were isolated from the sun, would look like that bar magnet picture. So the magnetic field lines are around the Earth. We're bathed continuously in this radiation from the sun. And then there's an interaction between the magnetic field from the sun in the solar wind and the Earth. So we're continuously being bathed in light from the sun, heat. But what isn't as obvious is we're also being bathed by particles, and there's a magnetic field interaction between the sun and the Earth. And in our atmosphere, there are atoms and molecules and ions in particular, and some ions, when they're excited, emit that green light. So the northern lights, the beautiful green light you see, is when there are ions in the Earth's atmosphere. And the source of the energy that was put into them for them to glow was the interaction between the Earth's magnetic field and all the stuff that's streaming towards us from the sun. Okay, that's an excellent question. The question was, why does that potentially cause power outages? So what you would get is, if one of these coronal mass ejections points in our direction, you would get an extreme change in the magnetic field in our atmosphere. And in electromagnetism, in fact, the person who's this phenomenon is named after is Faraday. If you change a magnetic field very quickly, it causes an electric field. So that induces a current, and anything metal will have a current induced and will melt, is the risk. So in when the Carrington effect happened, there weren't many electrical cables, fortunately, but what they did notice was telegraph. So telegraph lines are basically electrical conductors just held up. And when huge magnetic fields change quickly, they induce an electric field. The electric field induces current in the wire, and if you're unlucky, the current is so large it melts. So the 1989 Toronto, Quebec, North Canada, there was an electrical storm. It was so bad, it took down the power supply, and then literally cables taking electricity around. Toronto is a major city, and they didn't have, and it gets very cold in winter, and they didn't have electricity for the best part of a week. Basically because the electrical conductors that we see going from pylon to pylon, they're basically just sat there in space, and if there's a magnetic storm above them, the magnetic storm causes an electric field. The electrons in those cables oscillate too much. That's called heat, and the whole thing blows up, basically. Yeah. So if you see me and Steve running to Big Tesco to buy up all the tin foil, join the queue, basically. That's. If you knew this was happening, there's not a lot you can do with power cables. But there's other things like computers, other electrical infrastructure. You could actually say wrap in foil or hide. And if you knew 24 hours in advance, you wouldn't have planes in the sky, for example.
Yes. So one of the big issues now as well, it's not necessarily on Earth, but we're wanting to build bases on the moon and things. So it's very important that we can anticipate these things coming, because there's no interaction with the atmosphere there. We literally just fry the stuff on the moon. So it's something I hadn't considered until recently, but another major point of interest with this is, the fact we want to put more stuff into space and on the moon.
Thanks. Excellent question.
Yeah, it was an excellent question.
When's your bus picking you up? No, it's not that imminent. So, excellent. If you didn't hear at the back, the question was, how often do these things happen? When's the next one? So the sun has a cycle of activity. So in fact, some of our undergraduates take pictures of the sun safely and monitor those dark spots, those sunspots. They move. So if you take a picture today, then next Wednesday, etc., you can map out the motion. And in fact, the sun isn't a solid object. So the sunspots in the middle of the sun move at a different speed to the other ones. So on a 22-year cycle, the sun is very active, very quiet, very active, very quiet. And if you're at the trough, unfortunately, if that coincides with your 3 years studying with us, you don't see the sun. We have to give you pictures from 12 years ago. But in that period, when the sun is very active, what you can do is make a statistical prediction of how many coronal mass ejections you might expect this week. But that does it so, and that's a number of the order of a few. But they're random. So at the minute, the point is we can't tell you, is it going to happen today or tomorrow or by the end of the week. We currently can estimate roughly how many will happen. But if the coronal mass ejection points away from Earth, we currently don't care. If it points towards us, then you've got to worry about, and we're on an orbit and it moves around. So what we do know is if we had better data by visualizing these three-dimensional magnetic fields, we could start telling people we're very confident something really bad is going to happen, by the end of the week. So it's the power of having more data and powerful computers, actually. All of this is done now with machine learning, artificial intelligence, huge big supercomputers. So when I were a lad, if you watch the weather forecast, they might tell you today it's going to rain tomorrow, but you wouldn't, what up in Wales, the forecast was it was going to rain all week, all right. But you wouldn't believe what they would say about Friday, Saturday or Sunday, because weather forecasting was really hard. Now weather forecasts are much more reliable, and it's because of supercomputers. So people see patterns in clouds, isobars, and from that predict we might have a storm. It's the same with solar weather. people will take pictures of magnetic fields, and you'll be able to see, the last time this happened, 3 days later, something awful happened. So that's the idea, but it's a statistical game. It's not going to be an exact science of saying this will happen at this time. And they are happening now. There are coronal mass ejections. As Steve said, those sites, you can go and look at the sun now, but they also have an archive of interesting things that have happened.
Can I just follow up very quickly as well? So Pete was laughing about not getting scared. When I first met the solar physicist, it is quite scary, the stuff they're talking about. And like Ifan said there, these coronal mass ejections are happening all the time. But what you've got to remember is that Earth's actually a really tiny target in the solar system. So statistically, it's very unlikely that one of these things is going to hit us. And from our perspective as well, we're not just interested, so the model isn't just interested in looking for big events that might hit us. The beauty of it is we can analyse the disk of the sun and predict, all the flares that are going on, which will then help us to identify anything that's a bit more serious coming out.
Follow up.
How big are those solar ejections?
Oh, yeah. Do you want to get to
absolutely huge.
We have one image. There was a tiny Earth for scale in it. Yeah. The question is, how large are those stars? They're bigger than the Earth.
Yes,
one of your images very early on, Steve, has a
Well, even
Earth.
this image here, which is not showing a CME.
Oh, there it is.
You saw the size of flares that were coming off the sun. They were absolutely, or the CMEs that were coming off the sun. They were huge. And you can see the size of the Earth there. I mean, some of those prominences as well, those little arches and loops I showed at the start of the talk. Let me see, keep going. Yeah, these things here. So these smaller features here, you could fit many Earths in them. They're huge things. But still, in terms of when you're looking at intensity and density of the CME, those things are important. We're still a small target. These things don't come along very often, but they do come along, which is the important thing.
Can I just say thanks once again to Evan and Stephen.
Thank you.